Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's lecture. Okay. So, we will continue today with what we had, where we had left off in earlier class, which was discussing the applicability of ANOVA for linear regression. Okay. In linear regression. Okay. So, what is linear regression? You have data, right, and you wish to test whether there is a linear relationship between x and y, and you want to find out the expression of a line which best approximates that data. Okay. So, this data can be roughly written as alpha plus beta x plus some random error epsilon. Okay. So, this epsilon follows a normal distribution with mean of 0 and variance of sigma square. So, it is as if that on a line you have added a random error term at each point, thereby generating this scatter. Okay. So, we want to generate a line y is equal to a plus bx, which is called the best fit line. Okay. And the approach is using the method of least squares approach. So, in this approach, what you do is for each of these points, okay, you try to track the deviation of these errors. Okay. So, this is nothing but, so this equation, let us say if it is y is equal to a plus bx. Okay. So, you are in your least squares approach, you are minimizing sum of squares of errors, which is given by the expression summation of yi minus yi hat. What is yi hat? Y hat is the expression, is the linear equation of a plus b. Okay. So, you want to minimize this particular term SSE. Okay. And what you do, so what we have previously shown long back was using calculus. Okay, using calculus, you could determine the values of these coefficients in A and B. So, B is given by S of xy by S of xx, okay, where S of xy is given by summation of xi minus x bar into yi minus y bar. Okay. And Sxx is summation of xi minus x bar whole square. Okay. So, note that from our earlier definition we had the divided by n minus 1, which we have removed. Okay. So, this is the values of b, and you can write down the value of a. Okay. You can write down the value of a. Okay. You can, so again let me write, b is s of xy by s of xx. And a is given by y bar minus b of x bar. Okay. So, if this was true, so my total SS, okay, total SS or total sum of squares. So, again let me draw. So, you have this line, okay, and you have these points. Okay. This is your x, this is your y, and let us assume that when you do your averaging, this is your y bar value. Okay. So, your total sum of squares is going to be the deviation of these y values from y bar. Okay. So, in ANOVA, so this is your TSS value. So, you want to break down TSS into two components. So, TSS is component of sum of squares of regression. Okay. So, at each point, which is the sum of squares of regression? The sum of square of regression is essentially this component. Okay. Your sum of square of regression is essentially this component. Okay. From this deviation, what is the y term? Okay. This is your sum of squares of regression from this space. Okay. If the linear relationship did not exist, it's as if imagine all your data points were along the horizontal line, then this point from this base, how much is the deviation of this line, is your sum of squares of regression. Okay. So, how will I write down the expression for sum of squares of regression? Okay. So, once again, first let me write out TSS. Okay. TSS is summation of yi minus y bar whole square. Okay. SSR is summation of yi hat minus y bar whole square. Okay. So, once again, this is your y bar line, this is the line you fit, okay, and these are your points. Okay. So, this yi bar is this one, at every point this difference is sum of that is SSR, okay, and SSE, okay, SSE is this deviation from the line. Okay. So, SSE is given by TSS minus SSR. Now, if we expand on this SSR expression, so SSR is equal to summation of yi hat minus y bar whole square. Now, yi is given by the expression y hat is a plus b of xi. Okay. So, if I plug in the values, then what I get is a plus b xi hat, okay, b xi minus y bar, okay, whole square, okay, and y bar. So, we know that a is given by y bar minus b x bar. Okay. We can add plus b xi minus y bar whole square. So, your y bar and y bar terms cancel each other out, as a consequence of which you get SSR as b square summation of xi minus x bar whole square. Okay. So, your SSR becomes b square into xi minus xr whole square. Okay. And so, this you can rewrite as s of xy by sxx is what is b times this is nothing but s of xx. Okay. Okay. So, finally, you can write SSR as s of xy square by s of xx, and your SSE is TSS minus SSR given by, okay, SYY minus SXY square by SXX. Now, let us try to find out what is the degrees of freedom for each of those terms. Okay. So, degree of freedom of TSS. So, since there are n terms which contribute, okay, so your TSS is summation y across from I equal to 1 to n. Okay. So, your df of TSS is n minus 1. What is of DSS of SSR? Okay. So, SSR has this expression which is b square into summation of xi minus x bar whole square, right. So, all these xi and x bar are specified. So, you have only one degree of freedom coming from b. Okay. So, degree of freedom of SSR is equal to 1, which means the degree of freedom of SSE has to be n minus 2. Okay. And I can find out, okay, MSE which is equal to s square defined by SSE by n minus 2. Okay. So, this is the unbiased estimator of sigma square. Okay. So, this is the unbiased estimator of sigma square. So, if I write down the ANOVA table, okay, so your ANOVA table should look something like this. Okay. Source, degree of freedom, SS and MS. Okay. Your source is regression and error are the two components of the total. So, regression has degree of freedom 1, error has degree of freedom n minus 2 and the total is n minus 1. Okay. X. This is SYY minus X SXY square by SXX. This is SSR by 1. So, this is same as this XR and this is SSE by n minus 2. Okay. So, if let us say we want to find out whether the linear regression is at all useful or not, we can write down the test of hypothesis. Okay. You can write down the test of hypothesis as saying H naught is B equal to 0, let us say, okay, or you can in general you can say B equal to B naught and alternative hypothesis H A. So, for a one tail test, okay, you can write down as beta is either greater than beta naught or beta is less than beta naught, or for a two tail test, okay, you can find out beta as not equal to beta naught. Okay. So, for doing this we can use the student's t test, okay, to find out whether it is hypothesis is correct or not. We can use the t statistics given by the expression beta minus beta naught by root of MSE, okay, by SXX. Okay. So, this follows the t distribution, okay, because your standard of error is root of sigma square by SXX, and as we found that sigma square is the, so your MSE is the unbiased estimate of sigma square. Okay. With this, and once again as per the test, once you calculate the t statistics, if t is greater than t alpha or t is greater than t alpha by 2, so this is for the single tail test, or t is less than minus t alpha by 2. Okay. You can find out, okay, you can find out the p value, okay, and that would give us the final outcome whether your linear regression was at all useful or not. Now, for the case of linear regression, okay, for the case of linear regression, you can then find out how good is the approximation, okay, and we know that we use this term called R equal to SXY by SXXY, okay, as the coefficient of determination. This in our current language can be written as YY. Okay. So, now if you take the ratio SSR by TSS, what do you get? Okay. You get SXY square by SXX divided by SYY. Okay. And what is this? This is nothing but R square. Okay. So, you can say that R square is the percentage reduction in total variation obtained by using the regression line. Okay. So, R square is nothing but square root of r is nothing but square root of SSR by TSS. One other thing, okay. So in the general case, let us say imagine that x and y are not linearly related, but they are non-linearly related. Okay. Imagine that these are the points. So let us say this is the fit, okay, and these are your points of x and y. So if you were to choose only this domain, you would get a line which is something like this. If you have to choose a domain which is here, you would get a line like this, and if you choose the middle, you will get a line like this. Okay. So your range of data plays a significant role in dictating the validity of the model. Which means that based on this, if you are trying to estimate, if you are trying to extrapolate the data, you would incur huge amount of error. Okay. So this line would predict a value here for this point, but as you can see that this is clearly not linear in nature. Okay. So that concludes how you can make use of ANOVA. Okay. Oh, I forgot to mention one thing. Okay. After you do all of this, you can calculate the f value, and f value as MSR by MSE to determine whether your hypothesis of linear regression is good or not. Okay. So for the remaining time today, I will discuss about one other concept, which is the concept of block design. Okay. So when you do randomized experimental design, okay, this works very well when your sample is reasonably homogeneous. So for example, if you take a running race, what you measure would be very different if all participants were kids versus participants had both kids and adults. Okay. So this is what the aim of randomized block design is to do. Okay. So to take into account that you have various subpopulations in your main population. Okay. So in randomized block design, okay, so in randomized block design, instead, so you have k treatments. Okay, you have, so your entire population is divided into b blocks. Okay, so for the previous cases, you can imagine dividing your participants based on age. So each age would be a block. Okay, so there are b blocks, and there are k treatment means or k treatments. Okay. So there are n equal to b times k number of total sample size. Okay. So if you take an example, so imagine in a production line, okay, so the engineer is trying to compare between 3 methods for assembling a given product. Okay. So what the engineer can do, he can choose, okay, he can choose stuff, okay, where you can label them as S1, S2 dot S5, and each of these, okay, each of these participants, okay, each of these participants assembles using ABC, 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 but in random order. Okay, so on and so forth. Okay. So in this case, then you have your block are your staff, and your treatments are A comma B comma C. Okay. So, in this approach, okay, your TSS, so earlier you would write TSS equal to SST plus SSE, okay, but here we have one more time which is SSB, okay, sum of squares of blocks. Okay. So, I can write the TSS as before, which is summation of xij square minus summation of xij whole square by n, where n is equal to b times k. Okay. You can write down the expression of SST is equal to Ti square by b minus Cm. Okay. So, this is also called Cm. Okay. So, Ti square minus b, there are b blocks, for each block you have these many treatments. So, you average over that, okay. And SSB is given by summation of Bj square by k, where k is the number of blocks. Okay. So, SSB becomes Bj square minus Cm. Okay. So, the degrees of freedom for TSS is equal to b times k minus 1. The degrees of freedom of SST is equal to k minus 1, and degrees of freedom of SSB is equal to b minus 1. This would imply that df of SSE is b minus 1 times k minus 1. Okay. So, let us take a sample example and construct the ANOVA table for that. Okay. So, we had discussed the possibility of a pricing plan by cell phone companies for users of different ranges or usages. Okay. So, imagine there are 4 companies A, B, C and D, okay, and as per the usage level, can be low, moderate or high, and let us say you have sample rates at which they charge. Okay. Okay. So, as before, you can calculate the totals. So, you can calculate T1 as 403, T2 as 426, T3 as 408, T4 as 390, okay. And your G is the sum total of all these values, which comes out to be 1627. But what you can also calculate here, so you can also make another panel called totals here, and this is B. So, this is a block average, okay. B1 is 1055, B2 is 276, B3 is 1246. Okay. So, this gives you, so you have 3 blocks as per usage levels, low, moderate and high, and 4 treatments, or which are your companies and their pricing strategies. Okay. So, for this, you can ask, okay, so your B, is the number of blocks is 3, K is your number of companies, A, B, C, D is 4, N is 12. So, you have this total combination of 12 observations. Okay. You can calculate the Cm, which is given by G square by N. So, G we calculated the grand total of all observations. So, I can write down as 1627 square by 12. my sum of squares, okay, is just okay, is all these squares put together. Okay. So, you take the squares of all the observations, you can calculate SST. So, SST is T1 square plus T2 square plus T3 square plus T4 square, okay, by 3, okay, minus Cm. Okay. This is T1 is 403, so on and so forth. You can calculate SSB, which is given by, so SSB is these values, right. You have B1 square plus B2 square plus B3 square, okay, by 4 minus Cm, okay, and based on these values you can calculate the following ANOVA table. Okay. Your ANOVA table, okay, your source, okay, okay, you have two treatments now, usage and company. Then you have error, and then the total. Okay. This is 2, this is 3, this is 6, this is 11. So, I can calculate the values 5. Okay, and this is error. Okay. So, based on this, you can then probe the test of hypothesis for equality of treatments. Okay. So, your H naught is either no difference in K treatment means, or you can also have no difference in B block means. Okay. You can have these two cases. Okay. So, you can calculate your MSE as SSE by B minus 1 into K minus 1, okay, as an unbiased estimate of sigma square, okay, and you calculate the F statistics, which is given by mean square of treatments by mean square of error for calculating your hypothesis for treatments, or this is F of t, or F of B is given by MSB by MSE. Okay. So, if you calculate the value of F of t, this comes out to be 1.84, and F of B comes out to be 2351.99. So, this would say that your H naught, okay, is true. Okay. For treatments, your H naught is true. That means that there is no difference in the pricing strategy used by the different companies. But what you can clearly see, the FB value is way higher than whatever confidence interval F alpha you choose. So, this really means that H naught is not true. Okay. With that, I conclude my session today. So, what you saw was, what we discussed was how ANOVA can be used to test the whether linear regression can at all be used for fitting your experimental data. And then towards the end, we discussed about how you can make use of block design or randomized block design for quantifying or probing analysis of variance, where you have multiple subpopulations which exist in the population. Thank you for your attention.